Okay, class, I'm going to go over using Xfoil and Tornado for your final design project. I'm going to essentially go through the kind of computations you're going to need to do, so hopefully you find this tutorial useful. We're going to use Xfoil and MATLAB. Tornado's MATLAB-based software, although they have a Windows executable, which you may give a try. I don't use Windows, so I don't know how well it works. We'll look at these three wings here. The conditions are as follows. We have 8 meters squared surface area, or planform area. I just made some arbitrary cruise conditions, 75 meters per second to 2,000 meters. Notice this is different than your cruise conditions in your final project. Kinematic viscosity 1.73 e to the minus 5 meters squared per second, and I have a lift coefficient of 0.3, which is also different, a little different than your lift coefficient. We're going to look at the performance of these foils. I'm calling this the baseline. It's a simple kind of wing which meets this criteria as an aspect ratio of 8. It's a rectangular wing. Aspect ratio is just span divided by chord. 8 meter span, 1 meter chord, 2412 foil. This is an NACA foil, and no twists, no taper, and we'll see how this wing performs. Note that what we're going to do in Tornado is we're going to analyze a half wing. Because there's a symmetry plane here, Tornado doesn't have to analyze the whole wing, and we're going to establish this as put the geometry in as if it were a half wing, but we have to tell Tornado this is a half wing, and you'll see where I do that. Then we're going to go through two design perturbations or iterations. One is looking at this same wing plan form, but I'm going to twist it. I'm going to twist it -1 degree, meaning if the root is at 0, hopefully you can see my mouse, if the root is at 0 along the red line, the wing twists down geometrically by -1 degree, such that the tip is at a negative angle of attack relative to the root. Not necessarily relative to the flow, but relative to the root. It's twisted down to a smaller angle of attack by -1 degree. The last wing is going to have no twist, but it's a more complex plan form, consisting of two sections: a straight section from the root, the red line, to 2 meters out, halfway out along the half span, and then a tapered section with a taper ratio of 0.4 out to the tip. Now, when I say half span, I mean half the span. The full span is 8 meters of this wing. Half the span is there 4 meters, and I've divided it exactly in half. According to the rules in your design project, you may use a 2-section wing. These are 1-section wings because the wing has constant twist, constant chord, constant foil along the section. Therefore, we define it as 1 section. This is 2 because the taper changes from 1 to 0.4 between them. There are no other changes. Same foil, same twist, which is 0. This says 1. It should say 1.17 is the root chord, and obviously the tip chord is smaller than the root chord, and the root chord is larger than it is in the rectangular case to account for the smaller area out here. So what we're going to do is try to affect the loading distribution on this wing. Comparing the top wing to the bottom wing, you can see that there's more loading near the root. The root chord is longer compared to this root chord, and this tip chord is shorter compared to this tip chord. So if they're at the same geometric angle of attack, it should produce larger loading near the root and decreased loading near the tip. And remember, the downwash distribution, and thus the induced drag coefficient, depends on this loading distribution, which we want to be elliptic. This middle wing has a rectangular planform, but we've twisted this wing, so we've unloaded the tip of the wing relative to this, which means that in order to get it to the same lift coefficient, I need to be at a higher angle of attack for this wing than I do to this wing because I've unloaded the tip. Therefore, I've loaded up the root more than this wing and unloaded the tip compared to this wing. So in a way, this middle wing and this wing are similar. This is doing it using twists. This is doing it using a chord distribution. So I'm kind of curious to see what this does. I kind of made these up. This -1 degree is made up, but let's see what happens. So what we're going to do is let's first analyze these in Tornado, and then we'll go to Xfoil and get the profile drag coefficients as I asked you to do. So Tornado, I'm going to bring up my MATLAB. I've already put my path to, this is a Mac, I've already put my path to where the tornado was downloaded. Noting here I changed the directory name. Yours, once you unpack that file, it's T135 or some version number. I just renamed it to tornado, but you'll see T135 underscore something here. And once you're there, you launch MATLAB, and then I'm going to start tornado. And actually, I already have some files in here which I'm going to erase, and we will remake them. Okay, so tornado, when you unpack it, is a bunch of files, all sorts of code files that basically set up the lattice and make the computations and make some estimates of friction if you want to do that, although I prefer to do that in Xfoil. And all that code is in the topmost directory when you unpack it. You also have some subdirectory. One includes the aircraft. It comes with some aircraft. If you're curious, you can look at some of these. B707, for example. And when we make our design geometries, it will store them in this folder, and I'll show you that. I made this baseline, and I made, what did I call it? DO1. I guess I didn't save the other one, so I'm going to erase them. And then some other subdirectories include output, where we'll put the solution files, which will basically include everything: the geometry, the flight conditions, and all the calculations that are made by tornado, including the lift distribution, the CL distribution, the induced drag, some moments, a bunch of other stuff. So let me get rid of those. And then state. State is the flight conditions, and I will get rid of this. We're going to remake all of those. Okay, so those are empty. I've just started, I haven't started tornado. I'm going to start it. So let me clear my prompt here. Okay, so I'm going to start tornado by typing tornado. Okay, and it's kind of a little bit of a kludgy kind of menu, but once you get used to it, it's pretty good. And you can get around pretty quickly. So first thing we're going to do is make a flight condition, because that's the same for every single geometry test. So we're going to save it, we're going to make it and store it. Flight condition is basically angle of attack and altitude and speed, and some other stuff which has to do with maneuvering. You can do dynamic simulations within tornado. For example, it could be the aircraft could be rolling or pitching or yawing. You can look at the forces in those conditions. We're not going to look at those. So all those things will essentially be zeros. So input operations. Number 2 is flight condition setup. So I'm going to say 2. Okay, now I'm going to define a new state. Number 1. Okay, alpha. I'm just going to put 1 degree angle of attack. We're going to be changing this as we go along, so you could really put anything, but I'm going to put 1 because I know that's going to be around where I need to be to get my general foils to that lift coefficient I need, so it doesn't have to be perfect. Beta is a yaw angle, which is 0, no roll, no pitch, no yaw rate, no angle of attack change rate, no side slip, etc. Now I'm going to set the speed. There's a lot of units, there's a lot of options. We're going to go with option 2 is easiest for me because I have these two numbers in front of me. The true airspeed and altitude. So I'm going to put in type 2. I'm going to enter the airspeed, which for my case here is 75 meters per second. It's different for your project. Altitude 2,000 meters. It's different for your project. Now, it says caution, only use this option if you're really, really sure what you're doing. I don't know why it says that, but this is to apply the Prandtl-Glauert compressibility correction to adjust lift and other coefficients for Mach number. We're going to put 0. We're near incompressible with our velocities, so we might as well put 0 here. It won't really matter, but at least we know what we've done. Okay, so that's in MATLAB now, but it is not saved. So if I were to start MATLAB later, I'd have to retype all that stuff. So I go back to flight condition setup, number 2, and I save current state. And please note, I had not used Tornado until a few days ago, so I wanted to find a software that would work for the class, so I'm fumbling around a little bit. But save the current state here. We're going to save state as file. I'm going to call it MNE490 cruise. This is a map file. Basically, it's a MATLAB data file that contains the pertinent information that we just entered in. Angle of attack, flight speed, flight altitude, those kind of things. So that's saved, and now if I open up my little finder here, Go back to this directory, tornado. If I look in state, I'll see a file sitting there. That's the file I just saved here, mne490 cruise. It's a mat file. You can't, it's binary, so you have to only look at it through MATLAB, but it contains that information. Now what I'm going to do is set up the geometry. So I'm going to go for the first baseline geometry here, aircraft geometry. Setup 1. Define new geometry. 1. Number of wings. Okay, we only have one wing. 1. Number of semi-span-wise partitions for this wing. This is basically the number of sections of the wing. For our rectangular wings, I'm only going to have 1. For that last wing, you'll see I'll enter 2 here. 1. The wing can be defined by 1 partition. 1. These are reference coordinates for the CG and a reference coordinate for moments. We're not concerned about moments or CG for our project. I'm just going to put zeros here. It doesn't matter. This is an important one. Is the wing mirrored in the XZ plane? Meaning, are you providing me half the wing? Yes, we're providing half the wing, so it is mirrored. 1. Now, the root chord, they're not asking for the foil, they're asking for the chord dimension in meters, which was 1. The root chord is 1 meter. What's the airfoil? I'm going to put a 2412 in, and you can do any of the NACA 4-digit series. You can also do these other available airfoils here. There's some, you have to Google some of these, but some of these are sort of laminar airfoils. The SCs are supercriticals, probably supercritical airfoils, as we're talking about this week. Epler's, Clarkey's, typical, and there's an airfoil. I don't know what Vez's are, so you probably have to Google some of these. Base chord airfoil, 2412. Return. Number of panels chord-wise. Now I put in the project notes, I want everyone using the same, this is a discretization. Basically it solves this vortex lattice system by putting little panels on the wing and solving for the conditions of those panels. This is related to essentially the number of streamwise vortices, horseshoe vortices it puts on the wing, embeds into the wing. We want to use the same number here so we're consistent in class. So we're going to use a number that, at least on my computer, runs these simulations fairly quickly. And I did a grid convergence study, and this more or less stabilizes the lift coefficient and the load distribution. So I'm going to use 20 in the chord-wise direction, 20 panels. Now dihedral, I want you to put 0 here. A typical recreational aircraft is going to have about 3 degrees of dihedral. That gives you some roll stability. We're just going to analyze the wing as if it has no dihedral just to be consistent. Typically speaking, dihedral, of course, is going to reduce your lift. Some of the lift vectors pointed in and not actually producing up force. But it's a small number if you're talking a 3.5 degree dihedral. And I just want everybody to be consistent. So we're doing 0 dihedral. Now, number of panels semi-span wise. I want to use 20 panels across the whole half span of the wing. So for this wing where we're describing the whole half span using a single section, I'm going to put 20 here. You'll see for the last wing, which is tapered, I'll do 10 on the straight section, 10 on the tapered section. Here we go. I'm going to put 20 here. Span of the partition. Now this is the half wing, and it's going to be a span of 8 across the whole wing. Half the wing is 4 meters. 4 meters. Taper ratio is 1. It's a rectangular wing. Tip chord is the same, 2412. Now I asked you in your design project, you'll see in the notes that one of the constraints is you must use the same foil across the wing. You can twist the wing, you can mess with the planform of the wing, and you can change the foil, but you can't do what's called aerodynamic twist, messing with the foil shape across the wing. I'm just trying to constrain the design space a little bit. 0 chord line sweep, so there's no sweeps this wing, it's not necessary, and twist. This particular wing, the baseline has no twist, 0. Okay, now this is the other thing I want everyone using. How it basically meshes the wing. There's different distributions you can use. You want to typically cluster the panels closer to the places of action, which is the leading trailing edge, and wing tip. So that's what is referred to here as a span-wise, half cosine, chord-wise cosine distribution. I'm going to use that for all your wings. It's a distribution 3. So everybody's using 20 panels across the half span, 20 panels across the chord, and a span-wise, half cosine, chord-wise cosine spacing. Mesh type 3. Is the partition flapped? You can deflect a flap on these wings. We're not going to. We're cruising at the moment. 0. Okay, and we're done. And I'm going to save this now. I'm going to go back to the geometry setup. It's inside of MATLAB's workspace right now, but it's not saved for future reference. So go back to aircraft setup. One of the options is save current geometry. Number 4, save file as, and you want to come up with some kind of naming convention. I'm just going to call this baseline. I'll call it 490 for the class number. Baseline 490. Okay, so that's done. Now we're going to make a solution. Actually, let me plot it for you. So I'm going to go back up. We're in the geometry setup menu. To go back up a menu, it's 0, similar to Xfoil to get back and forth. I'm going to just plot this up. Oh, actually, I got to do one more thing before I plot it up. So that just defines the wing geometry. Now I have to define the mesh, and essentially it defines a set of horseshoe vortices are embedded in the wing at these panel points and stream downstream from the wing. So it's very important that you have your flight condition set up before you generate your lattice. Now we have set up our flight condition. I did not close MATLAB, therefore my flight condition is still set up in MATLAB, and I can check that when I look at the plot the wing. If you generate the lattice before you set the flight conditions, it assumes the plane isn't flying anywhere at 0 velocity, and it doesn't stream the vortices downstream. It's a little strange to me, but that's what it does. So I'm going to say 5, generate the lattice. Now everybody's going to be using the tornado method, which is default lattice selection 0. Okay, that's done. Let's have a look at it. With post-processing commands, command 7, I can have a look at the geometry, which is 2. It's going to plot a bunch of plots, which I'm going to have to pull into my recording window here. So let these go. Okay, so it's done. Let me kind of sort these out here. Okay, so these are a little redundant, but that's okay. So this just shows you my wing. Here's my reference point. Remember, I just put all zeros for center of gravity and reference points, so that's where I put it. The origin here, 0, 0. This is a plan view, and I have full span of 4 to -4, or 8 meters, chord 1 meter. This shows the actual mesh on the wing. I'm not sure I can zoom into this properly. Let me try zooming into this one. Okay, you can see how the mesh is such that you have larger cells or spacing here. As I move towards the tip, they get smaller, smaller, smaller. This is this cosine distribution. And if I go from leading edge to trailing edge, you can also see that they're clustering the panels. A given number of panels are getting clustered closer to the leading edge and the trailing edge than in the midspan. So if you have a given number of panels, that sort of defines the complexity of the problem, the runtime, the compute time. But by clustering them intelligently in regions of high gradient, you get a more accurate solution for a given number of panels. This one down here, excuse me, shows you the wing, and these are the trailing horseshoe vortices behind it, sketched behind it, established by this essentially 20 panels and 20 panels on the other side of this wing. And you can see how even these horseshoe vortices are clustered more towards the wingtip, which is where you have most of the vortex roll up. So this is a vortex lattice, or a VLM method of solving. It's an inviscid boundary method where you have to consider this wake sheet and how this it comes up with the distribution of this vorticity or strength of these little vortices in order to satisfy boundary conditions on the wing itself, done using a matrix inverse. Okay, so that's the geometry of our rectangular wing. You want to check that occasionally. You don't always have to check it. Let me go back to MATLAB. All right, so I can erase these figures, which I'm going to do. I'll go back to post-processing, result plot function 7. Option number 1 is just to clear plot. So let's clear those plots. Now I'm going to make a solution. I've generated the lattice, generated the geometry, and the flight condition set up. So it's called processor axis. There are a couple odd translations from the original language of the person who wrote this code, which I think is probably German, into English. So this processor axis may be one of those. But anyway, it's different solutions that you can make on the foil. So I'm going to go 6. And now, I want this foil at a given lift coefficient, not a given angle of attack. So there's two ways of doing it. I can run it at a whole bunch of angles of attack like we do at Xfoil, but that's going to be slow, and then I have to pick out the right one. So what I'm going to first do is find the alpha, the geometric angle of attack I need to get my lift coefficient. I'm going to let Tornado do that work for me. So I'm going to say 10, find alpha at prescribed CL, option 10. Now job identity, it doesn't seem to do anything, so I just put junk here. It doesn't seem to save any associated files, so I'm going to put junk. Now what's the target CL? For my case here it's 0.3, for yours it's something else. That's target lift distribution for the wing. Hit return, let it run. What it's going to calculate is the angle of attack needed for this wing to generate that lift coefficient. It should be 1, 2 degrees. Waiting. Okay, it's done. You got to kind of look up. Here it is. 1.8046 degrees. I'm going to just stick this, make another box there maybe. 1.8 alpha equals 1.8046 degrees. Go back to MATLAB, just check that that's correct. Okay, now I have to change the flight conditions to be at that angle of attack. I'm going to say flight condition setup 2. Now change angle of attack, it's one of the options. 4. Current angle is 1, that's the one we put it at. We're going to put it at, I already forgot what it is. Put it at 1.8046 degrees. It's possible there's a more efficient way of doing this in Tornado, but I'm unaware of that. Okay, that's going to set it. Now, I didn't save it into that file, my MNE 490 flight condition file. It's just it's modifying it within MATLAB right now. So now, we change that. Now, I'm going to regenerate the lattice. I don't know if this is necessary. It probably is not. It probably is based on the speed, not angle of attack, but I'm going to redo it. 5, and then, 1 second here, back up a menu, regenerate the lattice, 0. I'm going to use that Tornado method. Okay, it's done. Now go back to processor axis and we're going to run. We ran it at a fixed CL to get our alpha. Now we change the alpha, the flight condition. Now we're going to run a static computation at our state. Number 1. And we'll save this. We'll save this solution. Why don't we call it baseline 490 cruise. Let it run. So it makes a similar computation that it did when it was finding the alpha for the fixed CL. Here our alpha is fixed and is calculating CL and other stuff. Okay, it's done. Now we'll have a look at it. So I go to 7, post-processing result plot functions. Okay, so one of the options is static state. That's what we just saved. So I'm going to pick 3, and it goes in the statics in the solution, or the output directory rather. There's only one file in there, which happened to be the one we just ran. There will be more after we start doing more. Baseline 490 cruise. So forget about the CX. I'm just going to put in job ID as baseline 490 cruise, which is what I just specified before I ran it. And I hit return. It's going to put a whole bunch of plots up. Give it a second, and we'll go back through these. Okay, a lot of these are just numbers. You make sure your reference area ends up being 8. I'm not sure this will show up in the video, but there's a number here, 8 up on my mouse. This is 8 meters squared. Make sure that's correct, otherwise you didn't enter your plan form correctly. Now I'm going to pull this out of the way. There's some derivatives. This tells you, for example, the rate of change of lift with respect to alpha. So there's stuff like the lift curve slope right here, 4.638, in case you're curious about that. You could, in fact, use this to derive a, you could take your 2D lift curve slope from Xfoil and this 3D lift curve slope and your aspect ratio, and you could use that to derive, for example, a plan form efficiency factor. E. So now this is the first sort of important one. I see the drag here in newtons. I'm going to record you want to check lift coefficient 0.30013. It's very close to the 0.3 that I wanted. That's fine. And here's our drag coefficient. This is an inviscid method. It is calculating the inviscid drag, which is induced drag, 0.0036204. Put that here. Check that number, 36204. 36204. Let me hide my PowerPoint. Okay, so that's the induced drag coefficient. I don't need to store drag in newtons and the induced drag coefficient because I know my reference area, my flight speed, and by density at 2,000 meters, so I can get back. So I'm just going to store the drag coefficient rather than the drag. Now the other plot that I'm interested in, this is the shear force on the main wing. So you can see that the shear is maximum in magnitude at the root, and it goes to 0 at the tips as it's the shear force. This is a cantilever beam, so the shear force is maximum for this particular load at the root, and that's typical of a wing. Now I'm going to look at the next. This is a bending moment. This is the other thing you want to record. You got to count the dots, which I won't do right here, but essentially it looks to be about 5,700 Newton meters negative, but I'll just record the absolute value. 5,700 Newton meters. So again, it's a cantilever beam. Bending moment goes to 0 at the tip. Maximum at the root, magnitude 5,700 Newton meters. Let me stick that in my PowerPoint. Okay, and next is normalized CL. So this says if we normalize everything to a base of 1, it shows you, and this is good for comparing different wings. So we normalize the lift coefficient across the span from the tip at -1 to the other tip at 1. So the span is also normalized span station. And you can see this distribution looks kind of elliptic, but it's not elliptic. It's a little fat on the ends because it's a rectangular wing, which has a lot of chord at the tips. The tips are highly loaded, more highly loaded than an elliptical wing. So you get a more rectangular looking distribution. The lift has to go to 0 at the edges, and it doesn't quite show it here, but it's going to 0 at the edges. It would go if I had an infinite number of panels. So it has to go at 0 at the edges, but the more rectangular it is, the further away you are from an elliptical, truly elliptical distribution, which is what you want. There's normalized CL, there's actual CL here. Remember, 0.3 is where I set it. So that's the average on the wing. So inboard of maybe 2/3 of the way out, it's producing a higher CL than the whole wing, and the sections on the outboard side are producing a lower CL than the CL of the entire wing. And that's because they're experiencing greater downwash, and they're at a lower effective angle of attack, so they're producing less lift than the inboard sections, which experience less downwash, so they're at a higher angle of attack. We can also look at the span load. So again, the lift coefficient doesn't tell you the actual forces, right? So because the wing can have a smaller chord, this one does not. But if the wing has a smaller chord at the tips, having a higher CL doesn't times a smaller chord means you have, in actuality, less force. This is the actual force. This is in force per meter along the wing, and you can see the force is concentrated towards the middle. It's this integrated force that becomes the bending moment, and you can see how the bending moment adds up. As you move away from the root, you're adding force times distance, more force times distance, force times distance. That's integrated amount. You integrate under the area of this curve times the distance from the origin, and that's your bending moment. So this gives you essentially the load distribution on the wing. This load distribution we want to be elliptical. This is the span load distribution, and it's not elliptical for this wing. So we're done with this wing. What I'm going to do is exit out of Tornado as if we had stopped for the day. Now we're going to start up again. The first thing I'm going to do is load our flight conditions too. Load the state. There's only one state in there, MNF 490 cruise. Loading it in. Okay. Now we're going to generate a new aircraft geometry 1. Define new geometry 1. Okay, number of wings. Again, it's one wing. There's one span-wise partition for the first design iteration. Gravity, center gravity, x coordinate 0, 0, 0, 0, 0, 0. These things are not being used for anything useful, so we'll just make them zeros. The wing is mirrored, yes, 1. The root chord is still a meter. The foil is still a 2412. Number of panels chord-wise is still 20. Dihedral is 0. Semi-span-wise is 20. Span of partition is still 4 meters. Remember, this is the half wing you're putting in here. Half wing. The wing is mirrored around the fuselage or the root chord. We're only doing a half wing. 4 meters. Taper ratio 1 is rectangular. Tip chord airfoil is the same. No sweep. Now here's the change. We're doing outboard twist. I'm going to put -1, meaning the tips are twisted down relative to the wing. They're at a lower angle of attack relative to the root by -1 degree. And it does a linear twist between the root and the tip. -1. Okay, so mesh is still a type 3. No flaps and we're done. I'm going to save this, go back to aircraft geometry setup, save as number 4, and we're going to call it, I don't know, design 001 490. Okay. And now back up a menu. Okay. So first things first, we need to figure out the angle of attack to get at the lift coefficient I need. So I did load my cruise conditions. The first things first, actually I'm going to generate a lattice for this, type 0. Okay, so processor axis, meaning a computation. We're going to make a computation. Again, find alpha at the prescribed CL, number 10, same thing again. Job ID is just junk, I don't know what that does. Target CL is 0.3. Let it churn. It's trying to find out the angle of attack of this modified wing to generate lift coefficient of 0.3. Okay, it's done. 2.25 degrees. I think that should be larger than what we had last time. So let me start a new box here. Next to this wing. Alpha equals 2.25. Let me get a little bit more precise number for that. 2.251, so that was probably fine. 2.251 degrees. Now notice the angle of attack is larger than it was in the previous case, and that's because we've untwisted, we've unloaded the wingtip, so we need to load the whole wing up more to get it to the same lift coefficient. Now, 2.25, go back to MATLAB, change our flight conditions. Number 2, change angle of attack. Number 4, 2.25 is my new alpha. Now I'm going to redo the lattice again. I don't know if this is necessary. I'm going to do it 5-0. Okay, now we're going to go back to our calculations, processor axis number 6, and make a static computation at the selected state, 1. Let it churn for a while. Oh, I'm going to name it something, so I'll call it, what did I call the other thing? D001 490 cruise. So this is design 1. I'll just call 490, and then cruise. I'll note one thing before this is done. While this is churning, MATLAB doesn't like variables and probably file names that start with a number, so try to start with a letter. You can have numbers in it, but start it with a letter. Okay, it's done, so what I'm going to do is plot it. So I have a bunch of plots up. I want to close them. I'm going to go to post-processing. Number 1 is clear plots, so there they all go. Now number 7, and again I want to plot a static state, a different one than last time. Now you see there are 2 in here. My new design and my original baseline is still stored in there. So I'm going to load the new design, cruise. It's going to put all those same plots up. It's going to take a little while. Okay, so again I'm going to look for the critical plot, which is this one here, figure 7. The lift coefficient just shy of 0.3, 0.2998. That's good enough. Always check that because that makes sure that you're at the right lift. Now the drag coefficient is 0.03517. Let me put that in here. You can already see that we made a difference. We'll come back to that point in a second. Let's just check the bending moment. Bending moment is smaller, which makes sense too. It's at about 5,400. Again, you would have to zoom here. I'm not going to do it now. Zoom in and count the dots to get this 5,400. Call it. Okay, I put a bending moment constraint in your design problem. Otherwise, you would just let your aspect ratio go to infinity, essentially, and have your 0 induced drag. Which is not quite true because you start going to have more profile drag, but you would have too large an aspect ratio. It would be a silly looking wing. So the bending moment constraint is going to constrain the aspect ratio of your wing, but not necessarily your span. We can already see here, these are the same span. Let's just compare these 2 wings for a second. These are the same span, but I untwisted the tip here. So it's at a higher angle of attack, which is a little alarming. However, we have a smaller induced drag. I dropped it by about, how much? So about 3%. We have a 3% reduction in induced drag, which is going to end up being about 2% reduction, 1.5 in the total wing, which is a good thing just by this little twist. Our root section is now at a higher angle of attack, so closer to stall, which is something to think about. But I also reduced our moment, which means that I could probably get away with a longer aspect ratio with some twist to get a higher aspect ratio, less induced drag, and still be in my moment coefficient. That's because I moved the load, the span-wise loading, which let's quickly look at here. So bending moment, normalized CL, local CL, span-wise loading, and I'll compare the two at the end here, but the original load was much squarer. Now I've squished it so most of the force is on, the loading is on the near the fuselage and away from the tips. It's closer, it's not elliptical, it has a kind of fun hump to it, but it's closer to an elliptical distribution. So by taking the load away, I reduced the downwash is more constant. I wish this reported that. The downwash is more constant. We have less induced drag, and also reduce the bending moment, which means if we're given beam, essentially, we can have a little bit higher aspect ratio, which means we can get even more benefit. So twist can be good. Twist can also be useful to make sure that not just we have the lowest induced drag, but also we can ensure, for example, that we have stall occurring on the roots before the tips. So our tips maintain control even in stall conditions. We're not considering that in your design project. Your goal is least amount of drag. Okay, let's do one more wing while we're here. This is a little bit more complicated geometry, but I'm going to clear these plots. Did I write down my induced drag? I did. Okay. Put all the numbers in. One more geometry. I have my flight condition loaded at the wrong angle of attack, so we'll have to deal with that, but that's okay. So I have one geometry setup, new geometry, number of wings, still one wing, but I have two semi-span-wise partitions for the swing. Coordinates are all zeros. It's just meaningless. The wing is mirrored. The root chord, I forget what the number is. I'm getting, I think it's 1.1764. Hopefully I calculated that correctly. 1.1764 meter. It's a 2412 foil. Now, chord-wise, we still have 20 panels. No dihedral. Now, semi-span-wise, this is only for this partition. It's for the first 2 meters, just for this little block from the root to halfway out. So we want to use half our panels, and that half of the 20 is 10 panels. The span of that little section is 2, right? 2 meters. Taper ratio is 1. It's square, rectangular. Actually, it's rectangular, yep. Tip chord airfoil, that's the tip of that section. It's not the tip of the wing. It's the tip of that section here. But we're using the same airfoil throughout, so this doesn't matter. Come back here. It's a 2412. Oops. Now, quarter line sweep. I have no sweep, no twist. Okay. And a span-wise half cosine distribution, and there's no flaps. Okay, now we're on to the next partition. This is referring to the next part of the wing, which is the tapered part of the wing. Dihedral is 0. Semi-span panels is 10. I had 10 on the inboard, 10 on the outboard. Span of the partition is 2 meter. Taper ratio is 0.4. Tip chord is the same, 2412. No sweep, no twist, a mesh type 3, no flaps, and we're done. I'm going to save this. I'm going to go back to geometry setup, save as number 4, and we'll call it design 002 490. So I have 001 490. Go back up to the main menu. Okay, so now we're ready to generate the lattice 5, 0. Type 0. Okay, now we're going to do our computation. Let me clear any plots I might have. I'll do that later. My computation 6. I'm going to do a fixed alpha for prescribed CL, which is a type 10. Job identity is just junk, and 0.3 is my lift coefficient. Let this churn for a little bit. And okay, it's done. Alpha is 1.6882 degrees. Come back here. Is that right? 1.6882 degrees. That's correct. Okay. Now we'll change our flight condition. For this alpha 1.6882. Okay, that's done. I'm going to redo the lattice, although that may not be necessary. and I'm going to now run this static computation at select state number 1. This will take a second, and I want to save this, so I'm going to call it design 002 490 at cruise. Solution started. Okay, it's done and saved, and now we'll go post-processing or clear plots. I don't think I have any plots to clear. 7, 3. Now I have 3 options in here. I'm going to load my this case and let it do all its plots. Here they come. Some of these, you'll note, you might have seen that they already look a little different. Come back here. Make sure the lift coefficient is correct, 0.300. That's correct. Drag is 0034911. Man, my memory is going. 391 34911. Let's try that. 34911. Okay. All right, and then we come back here to the foil. We'll have a look at shear force. You see these little bumps? That's where the taper obviously is. Bending moment is smaller. It looks to be about 5,300, 5,250. Okay, smaller moment, that's a good sign. And now, one more thing I'll show you. Let's have a look at, now these lift coefficients, they look a little funny, but it has to consider every by section. It looks at a lift and by section. Depending what it's using for a chord to normalize it, it might cause these inflections here, which may not really be real, because when you get to the load distribution, it just has a tiny wiggle where the taper jumps occurring, where the section's changing from a rectangular to straight. So this is closer to an elliptical section. So we tricked the wing, similar to the Cessna 172, into thinking it's an elliptical platform by giving it a 2-section wing, a taper on the outside and a straight section on the inside, and that's the result. This is the wing. You can clearly see that it is tapered, and you do want to have a look at this to make sure that you do have that the wing was entered correctly, and you can see it's kind of a funny wing, but essentially it looks like in the panels. And this gives you the pressure coefficient distribution as well on the wing, and you can see you have the higher. I don't know if I can renormalize this from here, but you have the maximum suction occurring here towards the leading edge of the foil. The flow's moving this direction. Okay, so this is done. Let me just plot 2 of them against each other, so we can see the difference. 7-1. Now, one issue with this is if I'm gonna load. So I'm done. I could be done for the day. I could exit Tornado, and I'm gonna start up MATLAB again and go back to Tornado. I start it up. Now, if I just want to, I have my geometry in here. If I want to reload my geometry and rerun it, I can do that by just typing 1 geometry setup, load geometry, and load up the geometry. I could do that. I'll do it 490. So now it's in there. I can also load in my solution file. So I go 7, 3. So let's compare our baseline. Let's compare the baseline. Okay, so no such job ID, and that's because when I copied and pasted, I included a space in there. Tornado's a little picky about spacing, extra spaces, so let's just do this again. 7-1, we're going to do 7-3. I'll type it in DO on a baseline, 490 cruise. So it's going to put all those plots up. Okay, if I leave them open and I load another file name, 7-3, and I load DO01, let's just compare the first and the last. 02, 490 cruise. So this is straight planform, no twist, and a planform, straight planform / tapered planform, no twist. Same foil section, same lift coefficient, and this will go. Okay, now the line colors are not different, so we have to discriminate between them. We can clearly see the little jogs here, so you can tell which is the 2-section wing here. here you can't see it, but I know the answer because we wrote down the bending moment. The bending moment of this wing with a smaller magnitude of bending moment is the tapered wing, the wing with taper. This is a straight wing. And if I go, you can clearly see the difference in the lift distributions. This isn't too useful. Let me go out to here. Now, this one that's sort of bowed out or squished down is a rectangular wing. You can see there's larger load near the tips, and you have the force, and then on the inboard side it's less. In the tapered case, we have a larger root chord and a smaller tip chord, so it manipulates this distribution into this distribution. You say, why is it a great distribution? Because closer it is to elliptical, the closer we are to this conditions of minimum induced drag based on Prandtl's thin wing finite aspect ratio theory. And we were able to make this. And if you look at the progression of our situation from rectangular to rectangular twisted to this kind of thing, which I pretty much made up but ended up being okay, we go from induced drag of 36 counts, 35, 34, almost 35. So there isn't actually that much different. There's a greater difference between our rectangular wing and the twisted rectangular wing than there is between the twisted rectangular wing and the tapered wing. So this twist is kind of like taper in a way. So you can mess with the load distribution in different ways through twist, which geometric twist, aerodynamic twist, which is modifying the foil shape, typically camber, which we're not doing in this project, and planform shape, which is this. So you're going to be messing with 2 of the 3 potential options to mess around with the load distribution. We're not done yet. Let me pull up Xfoil. I think I got to keep this open. Xfoil. Let me grab my terminal. All right. So if I start Xfoil, now what I'm going to do is I'm going to, and I put the run commands that you really need in your project file. They're pretty quick. So we're going to do NACA 2412. What I want to know is what's the profile drag on the profile drag, estimate the profile drag on the structure. And what we're going to do is base it on the profile drag experienced by a wing section running at the Reynolds number that's representative of the mean chord, which I have to compute for this, and running on the, and at the lift coefficient of the entire airplane wing. Now, note that different sections are really running at different lift coefficients. You can see here, and we know from Xfoil that there's in a certain region at low levels of lift that the drag is pretty constant, and that's because it's really based on Reynolds number. You don't have a lot of profile effects. As you start to go a higher angle of attack, the drag starts to rise. So you start having a CL-CD relationship. We're sort of on the edge of that, so there's some CL influence on our drag coefficient. But you can see that the wings are, different sections are at different CLs. So really what you'd have to do is use Xfoil to integrate this entire distribution. You have differing Reynolds numbers, differing lift coefficients, different chords, etc. So getting at the actual friction is tricky. Xfoil could do it in sections, what they call strip theory, or you could run a real 3D code, which would include also, in addition, the span-wise velocity field, which is particularly pronounced on a swept wing, unlike this case. But we're going to do a simple way, exactly as I outlined in the project. For our first wing, we're going to bring Xfoil back. It's a NACA 2412. I asked you to adjust the paneling, which I won't do here, but the commands are in the project description, as you did in your computing project, to just add a few points to make a more dense paneling. Let me skip that for the moment. I'm just going to go right to setting the operating conditions. Oh, I need to know what the Reynolds number is. So let's do that first. Let's get out of here, and I'll use MATLAB. So if I go back to my PowerPoint, this rectangular wing, the chord is 1, nu is 1.73 e to the minus 5, and velocity is 7.5. So 75173. So my Reynolds number is 7.5 times 1 meter over 1.73 e to the minus 5. Okay, it's 4.33 e to the 6, 4.33 million. That's about the Reynolds number we've been working with in class. Visc, 4.33 e to the 5. I'm not going to change any of the free stream turbulence, blah, blah, blah. Let's just keep that the default. Now, I just want to know what this thing does at a given lift coefficient. I'm not going to do a polar or anything like that. I can just say CL. Did I do everything? Let me just put iter 100 to make sure it converges. CL 0.3. That's the lift coefficient in my demo here. It is not the lift coefficient for your project. Just note that. Let it rip. Okay, there's a wing, and I'm going to also make note, approximate note of where it's transitioning. Transitioning about on the upper surface 10, 20, 30, 40, 50, 60, 70. It's 70% of the chord. Check these numbers. 70% right lift coefficient, correct Reynolds number coefficient. So this is essentially an average boundary layer over the wing, our baseline wing. Drag coefficient is the most important thing. 00683. Let me grab my PowerPoint. 00683. Okay, and what was my other thing? X over C trans was 70%. Okay. So this tells me right away that my profile drag's not double, but it's close to double my induced drag, right? So I want to be messing with both of these. I want to find a foil that has a good profile drag and one that has a good induced drag. Now I did put a thickness constraint on your thing. It has to be, the thickness to chord ratio has to be 12% for the foil. So you can't go in and use a super thin foil. Keep in mind that you're designing a wing. You're not caring about stall, about this thing at takeoff, how good it is in a variety of conditions. So in reality, a good designer would tweak this wing and it might end up being kind of an impractical shape, and that's fine. If you guys find yourself marching towards an impractical shape, that's fine. That's the way it is. And normally design has to be done using a multi-point design, essentially weighing different points. It's got to be able to do this and do this well, and kind of weighing those two factors. We're designing for one design point, and in the world of aerodynamics, you can end up with some weird stuff. So if you get forced in a weird direction, that's fine. Just try to be able to explain it. Let me go back. Now, our other wing, this wing is no different. The chord's the same, the Reynolds number is the same, the lift coefficient is the same. So the CD for this one is also going to be exactly the same. We're not changing anything. X over C trans 70%. Okay, in lieu of time, I'm not going to sit here and compute what the mean chord of this is. We could do a little algebraic computation. This chord is going to be close to 1 anyway. Actually, it's going to be exactly 1, isn't it? Because to get the right surface area and the mean chord for the same span, it is the exact same. Mean chord is exactly the same, and the flow speed is exactly the same. The altitude is exactly the same, therefore the kinematic viscosity is the same, therefore the Reynolds number is the same, the lift coefficient is the same, and therefore CD is the same. Okay. And I knew that only because I had the same reference area, same planform area, same span, therefore the reference area is the span times the mean chord. That means the mean chord is the same, and I'm basing my profile drag off a mean chord. So so really we haven't changed the way we're calculating it, the profile drag. Probably will have some realistically would have some profile drag variations here. However, they would be difficult to capture without using a real 3D viscous solver, which we do not have at our hand. So we're going to use the method we have. And you can see in this case, if you want to keep the span the same, it's your job to maximize induced drag. But we can see here that the moment is dropping. We can push this last foil out, probably increase the aspect ratio a bit, make a bigger span, a smaller chord, which should reduce the induced drag. It's a higher aspect ratio. But the smaller chord means we've got to go back and do our profile drag computations because the Reynolds number has dropped. Now note, our Reynolds number drops, but that means our drag coefficient goes up. Remember, this viscous drag coefficient goes up with decreasing Reynolds number. So, and remember, the shear stress distribution over a foil from front to back is highest towards the front. So when you have a shorter chord, you actually, in a given area, you end up with higher shear stress. So making a longer, skinnier wing might be better for induced drag, but it might be worse for profile drag. So you may end up with some kind of trade-off, and eventually you're going to violate that bending moment coefficient. Probably you want to push the bending moment constraint pretty hard, because that's going to get you to higher aspect ratios. And realistically, these wing designs are trade-offs. The higher aspect ratio is better in terms of induced drag, but you have fighting structural issues, essentially. I put it in as a simple constraint, which is two constraints: a bending moment maximum at the root, and number two is a thickness to chord constraint for your project. So that's it. Hopefully this will guide you. Pretty much just follow what I did and perform your design, but do it more intelligently than I did. Start with your baseline. Use what you know about thin wing theory, about viscous drag, profile drag, dependency on Reynolds number and chord, induced drag depending on the planform shape, why twist would matter, these kind of things to guide yourself towards an optimal design. I want to see you exploring the design space in an intelligent manner and see what you end up with.